Do you have a hard time trying to sleep? Do you experience shortness of breath and after waking up, extreme drowsiness and lack of energy during your whole day? We have the solution just for that.
Our solution will help you diagnose sleep apnea, consult doctors, and also generate reports.
Our system comes with multiple sensors, an airflow sensor, two strain sensors, and an SpO2 sensor to detect all your airflow and breathing patterns along with your oxygen levels. After a good night's of sleep, the data recorded from these sensors will be sent into our app. This app can be used by the patient and the doctor as well. After logging into the app, you can go on to the signals page. The signals page will have four types of signals: SpO2, airflow, thoracic, and abdominal movement. Each of these signals will have apneas detected and annotated in red color. And after viewing and understanding your breathing patterns, you can move on to the report section where you can generate a PDF report and save it in your local folder system. Also, the doctor or the professional that you are under will be assigned in the app, and this professional can view these signals and provide a diagnosis and recommendation to improve your sleep also. The recommendations and diagnosis given and updated by the doctor will also be reflected in the PDF given to you.
Hi, we have a volunteer for our apparatus. Let's go into the details. The first thing here is the strain sensor, which will measure the thoracic movement of the human, and this is the strain sensor for the abdomen pressure.
And this sensor is used to measure the airflow while the user is breathing in and breathing out. And any drop in airflow will be recorded through the readings of the sensor. Then in addition, we have an SpO2 sensor which will read the oxygen saturation levels in his bloodstream. And depending on the airflow and blockages in his throat, this will also give us a signal.
And that is a microcontroller which we are using to get all the data.
So we have used an ESP32 Rover model, and it has 8 MB flash RAM. So we made sure that all the data during sleep will be recorded, and even if it's 90% full, we'll send it to the server and restart recording. So that's the whole setup. Thank you.
Thank you for watching. Welcome everyone. The title for our project is AI Assisted Diagnosis and Management of Sleep Apnea. And the teammates are myself, Jaisuraj Bantupalli, Amal John, and Adnan. Moving on to the next slide. Sleep apnea is a very serious challenge in the real world. So the current approaches are like having PSG, which is having a huge setup, and there is a lack of simple portable home appliances to detect ourselves from sleep apnea and diagnose it. So the problem right now is that there is a lack of portable devices, as well as there is no instant check for the sleep apnea diagnosis. So what we wanted to do is, coming to the proposed solution, what we did is we've made an entire system which will detect the sleep apnea, and the user can also visualize it in an app. So what we did is first we collect the data with the hardware. Then, with the help of microcontrollers, we send it to the server. From the server, the backend will process wherever the apneas are present, if present. And every detail like AHI index and everything will be sent it to the app, and app will be used as an application interface to visualize all this. So basically, what I told is the project outline. And coming to the next part, the front end part. Um, we used a Flutter framework to build the front end. Authentication of doctors and patients is done using MongoDB database. And we also made process easy for doctors by already creating the reports using backend. And also we shows graphs in applications to visualize what point of sleeping, the breathing had obstructive sleep apnea, central sleep apnea, or hypopnea. And coming to the next slide, we showed apps. Here you can see that In airflow, abdomen, SpO2, and thorax levels we are taking. So what we are doing is like the app, you can visualize, patient can log in and visualize any one of the waveforms, and you can see the data graph, right? In that, he can visualize it like this, like previous 500 data or next 500 data or full graph all at once. The app also has a login for doctor where he can see all his patients listed, and whichever patient he wants, he can go click on them, and he can also write whatever he wants and recommendations and give the AHI index as well while report generating. So what we thought about possible improvements in application side is that we can actually put a chat screen for online consultation and payment gateways also, so that direct appointment bookings with the doctors and all can be done easily. Subscription users might have different perks. So all these features we wanted to, we thought there can be a possible improvements. So coming to the next slide, the backend part, the server is built with Flask. The authentication, as I mentioned, the API endpoints are defined in the Flask application, and all of the user data will be stored in the MongoDB. And also, the server will process the entire backend model of apnea detection as well. Amal will take over Cat 22 feature extract.
Yeah, so the primary algorithm we have used here for the classification of, and detection of apneas, a cache-generative feature extraction along with random forest algorithm. So what cache-generative feature extraction does is it's built upon a precursor algorithm called HCTCA, highly comparative time series analysis. So HCTCA has 7,700 features approximately, and all these features is not necessary and is very hard to process at one run in one run. So what Cash22 research did is it tested 7,700 features extracted from various time series dataset and checked how those features performed on different classification and prediction tasks. And based on the performance on these tasks, they selected 22 features which provides the most amount of. Now, this is the methodology followed by the precursor paper, cache-native feature extraction. So we can see how they collect all the features and get the accuracies of different features combined into classification and prediction model. And that is how they figure out what the best features are and what features provide the best results. And this is the system architecture one. So we have two architectures for obstructive apnea and detecting all kinds of apnea. In obstructive apnea, we have grouped the data into subsets of airflow, SpO2, and annotations only include obstructive apnea or not obstructive apnea, and that will be the result that we get. So this cluster data will be going into the cache 22 feature extraction algorithm, and all the 22 features will be extracted and made into a data set, which will be the X or the training data set. And this training data set will be put into a random forest classifier model, which gives the classification into obstructive sleep apnea or not obstructive sleep apnea. The, arch- the architecture 2, on the other hand, can The architecture 2, on the other hand, can classify between three classes, which is obstructive sleep apnea, central sleep apnea, and or no apneas. So here the nasal airflow, abdomen movements, and thoracic movements are taken, and these data is clustered into groups of apnea, of obstructive apnea, central or no apnea, and these clusters are put into a cache 22 feature extraction function, and all the 22 features will be extracted. This will be later used to train a random forest classifier model, which can predict if the given region of sleep or time series data of sleep has obstructive sleep apnea, central sleep apnea, or no apnea. So before fixing on Cache 22 algorithm, we tested on various other algorithms for feature extraction or time series transformation. And what we tested was Boxcox and binning algorithm. So Boxcox algorithm made sure that the randomly distributed data which we have will be converted into a normal distribution, which is more readable or understandable by the classification model. And similarly, the binning discretizes a continuous waveform. So we have a continuous signal of time series, and this time series signal will be discretized by changing into 0, 1s, and minus 1s, or 0, 1s, and 2s based on the location of the value. And this will make it easier for the model to understand, because there are only three unique values, which are just lows, highs, and mids. And we also check differential and Hilbert transform. Differential just gives the difference between two regular periodic points to get a better waveform. And what Hilbert transform does, it gives the upper envelope of the waveform. So, for example, if you have a waveform with varying signals, it just creates a signal along the upper peaks of your waveform. So you get the increase and decrease of airflow in the output waveform. And the output, so the results we got from our iterative experimentation was that Cashmere provided 94.87% accuracy. Meanwhile, Hilbert was the other second most accurate one, which was lagging behind at 91.28. And every other algorithm we used provided less accuracy. So we figured out that Cashmere is the most ideal algorithm which we found. Then what we did was, after deciding on Cash22 as the most accurate algorithm, we tested which classification algorithm among random forest, gradient boosting, KNN, naive Bayes, and SVM has the best performance. And after iterative testing, we found out that accuracy of 94.87 was received in random forest algorithm, while everything else lagged behind at 90%, 82%, 76%, and 89%. Now, possible improvements on this mechanism is that we can explore the possibilities of explainable deep learning models, so which will have support for more variance in data along with explainability of the outcomes. Then, since we are deploying an app and recording data of users, we can reuse the collected data from the users, which are later annotated by the professionals, to retrain the app to adjust for different kind of audiences, different types of user from different areas in the world. And this is the one of the best possible improvement that we can think of, because as we experienced while doing our research, data is something very hard to get by in this field. And even when we get data, the sensors are not always similar and won't always give the same output as we get. And yeah, that's one of the possible improvements. Now my teammate Adnan will explain all the hardware parts that we have used for this project.
Now coming to the hardware part of the project, we are using a microcontroller ESP32 Grover, which has a built-in Wi-Fi and Bluetooth and has an internal memory of 8 MB. It helps us to manage and store the sensor data, and it helps us for communicating with the server to transmit the data. The four sensors which we are using to our project are strain sensor, pulse oximeter, and airflow sensor. Strain sensor helps us to collect the data from the abdomen and thoracic, and pulse oximeter helps us to collect the data of SpO2 values, and airflow sensor, which is a pressure sensor we are using, which helps us to calculate get the nasal airflow. It is a lightweight sensor, and the response time of the sensor is 5 milliseconds. The possible improvements are basically we can use high performance sensors, which can be custom made or to get better accuracy, and it will help us to read the body movements and the postures properly, and will give a comfortable fit eventually. Thank you.
So, So that concludes our demonstration and presentation of our projects. To get further details of our project, we will provide links to our reports and diagrams and methodology in the description below. Thank you for your time, and hope you have a nice day.